So in this video we're going to look at finding the equations for tangent and cotangent functions that have been horizontally or vertically stretched or compressed by looking at graphs of those functions. So the key is to look at the graph that you have, and if it is a graph that can be modeled using tangent or cotangent function, your job is to decide which of the two functions is going to most easily be used to model it. You can always use either of the two to create a model, but frequently it's going to be the case that one of the two more easily fits the situation at hand. And the key is to remember what the tangent function looks like versus what the cotangent function looks like. So the tangent function for the y-axis has vertical asymptotes evenly distributed to either side of the y-axis, whereas the cotangent function has as one of its vertical asymptotes the y-axis, and then to the right of it at pi radians there's another vertical asymptote. So here, when I look at the situation that we have, I see that I have vertical asymptotes evenly distributed to the left and right of the y-axis, which means that the tangent function, is going to be the easier choice. And then I want to remember that the tangent function has this basic shape to it. So the shape that I see right here is matching this basic shape with no need to reflect over the x-axis. If I had something that looked like it was coming down this way, I would say, ooh, I need to reflect the tangent function. But I have something that's really naturally going to fit with the tangent function. So we're going to go ahead and start setting things up. We're going to say, hey, I'm going to model this using the tangent function. So we have a t-axis, so I'll try to be consistent. And it's going to look like this: a times the tangent of bt, because we don't have any vertical or horizontal shifting. To figure out what b is, what I need to do is look over here at this vertical asymptote and say, hey, it's located at pi, right? The input is pi, t equals pi when I get a vertical asymptote. And then I want to think about the toolbox function, and where is that first vertical asymptote to the right of the y-axis located on the toolbox function. And for the toolbox function, it's located at pi over 2 radians. So what I want to do here is say, when I plug in t equal pi into my tangent function, so I get b times pi as an input to my tangent function, to get a vertical asymptote, it needs to generate a value of pi over 2, which is the location of the vertical asymptote on the toolbox function. And now I just solve for b to figure out what value of b I need to make in order to make that happen. So I get b equals 1/2 after everything cancels. And what I did here, just in case that didn't make sense, I know that to get b by itself I could divide both sides by pi, but that would create a complex fraction here. And so to avoid having to deal with a complex fraction, I take advantage of the fact that if I have a number and I multiply by its reciprocal, the product of reciprocals equals 1, so these cancel, giving me a 1 times b is b. And then when I do what I do here is I multiply by that reciprocal on both sides. Pi divided by pi is 1, giving me the 1/2. So I can come to my function right here and I can say this b needs to be 1/2, so that when I plug in pi, I get pi over 2, the location of the vertical asymptote for the toolbox function tangent of theta. So then my next job is to figure out what a is. And what I want to do is look at the graph and identify whether it's been broken in, whether I can break it into 4 equally spaced regions. In other words, if I put a tick mark here, here, at the asymptote, here, and here, is that breaking the graph into 4 equally spaced regions? 1, 2, 3, 4. And if it is, I can take advantage of that key point on the toolbox function, where we know if we plug in pi over 4 radians, the output is going to be 1, because at pi over 4, x and y both equal square root of 2 over 2. So the ratio y over x is going to equal 1 at pi over 4 radians. And I see that I have equal spacing, so I know that this is usually a 1 right here. And because it's a 1, I see that I had to do 3 times 1 to get 3, so I know a has to equal 3. If you feel uncertain about doing that, if you feel uncertain about scaling it that way, you could leave it as an a and just plug this ordered pair into the function. So I could say, hey, the function output is 3 when the input to the tangent function is pi over 2. And then I could start simplifying. I could say 3 times a times the tangent of 1/2 times pi over 2 is pi over 4. And then I look at this and I say, I know what the tangent of pi over 4 is. The tangent of pi over 4 is actually 1. So I see that 3 needs to equal a, and then I could go back to my function and update it with the 3. So we could solve for a, or we could use what we know about key features on the tangent graph to come up with a in this particular case. So if we look at one final example, again the idea is look at the tangent and cotangent toolbox functions and see which one this situation more closely resembles. And in this case it's more closely going to resemble the tangent function, because it's cotangent function, because the cotangent of theta as a toolbox function has a vertical asymptote as the y-axis and a vertical asymptote to the right of the y-axis. And that's a situation I have here. I have a vertical asymptote here, and here I can model it relatively easy using the cotangent function. So I'm going to make a function of t, because I have a t-axis. I'm going to say I'm going to model you using the cotangent function, so it's going to be cotangent of b times theta. And then we can start to figure things out. Usually on the cotangent function, not usually, always for the toolbox function, this vertical asymptote is located at pi radians. We know the tangent function sweeps down like this, so I don't need to do any reflection in the t-axis. This is usually at pi radians. This first vertical asymptote is located at, this is 1 right here. There's a 1, so these are broken into 1/2, so this is 3/2 right here. So when t equals 3/2, we get the first vertical asymptote to the right of the y-axis. But on the toolbox function that occurs at pi radians, so that should be a t, because I have a t-axis and a function of t. So when we plug t equal to 3/2 in for t, we need b times 3/2 to equal pi, the location of the vertical asymptote on the toolbox function. Multiply both sides by 2/3, and we get b equals 2 pi over 3. And I can come up to my function and update b with 2 times pi divided by 3. And then we just need to figure out what our value for a is. And in this case we're going to have to do a little more work, because between here and here, if tick marks are evenly spaced, the first tick mark, which would correspond to a nice point on the cotangent function, so at pi over 4 the cotangent function generates a 1. So if I look here, I have 3/2. If I take a quarter of 3/2 to figure out what this first tick mark should be if things are evenly spaced, I would get 3/8. So usually you would have 3/8 and a 1, but here the point I'm given is not 3/8. So this isn't a point that's falling equally into 4 equally chunked spaces. So I'm not going to be able to use a special point on the cotangent function that I know offhand. We'll need to plug this point in to the function. So I'm going to take the known point on the graph. The output f of t is 2 root 3 when t is equal to a quarter. So I'm going to plug in that quarter, and then I'm going to simplify, so I get 2 square root of 3 equals a times the cotangent of, this is going to simplify to pi over 6, and then I recognize pi over 6 is a special angle, so I'm going to go to my unit circle and recognize that pi over 6 or 30 degrees is equivalent to 30 degrees, corresponds to the ordered pair on the unit circle root 3 over 2 comma 1/2. And I know that the cotangent function is the ratio x over y. So in this case, x divided by y, the 2's would cancel, giving me root 3 over 1, or just the square root of 3. I get the square root of 3. So I get 2 square root of 3 equals a times the square root of 3. Divide both sides by the square root of 3. I get 2 is equal to a. So I can come to my cotangent function and update the a with 2. And there I have my model for the cotangent based on the graph.